Welcome, everyone. Today we are very happy to have Nat from Caltech, who did a lot of interesting work about topological basis matter and overlap with computation. Today, Nat will tell us about Floquet codes, TQFTs, automorphisms, and computation.
Yeah, thank you for everyone for coming. Today I'm going to be talking about some work I did while I was visiting recently at Microsoft, and it's work regarding a new kind of quantum error correction code called Floquet code. And this Floquet code has appeared in the last couple of years. And one of the things we were trying to understand is how to sort of connect it to notions we've been establishing between, for example, quantum information and condensed matter and high energy, the relation between error correcting code and TQFTs and phase of that. So, so just before I begin, I just want to thank my collaborators. So this work was done in collaboration with Margarita and Dr. Subramanian. They are both grad students at MIT, and Dave Mason, who is at Microsoft. And this is based on two works, one which I did last year with Margarita and Shankar, and then more recently the work I'm going to be talking about is collaboration stage. So just to set the stage, I'm going to be talking about quantum error correcting code. And in quantum information, the basic building blocks of why we want to create these codes is that suppose we want to build a quantum computer in the future, your information might become corrupted by some noise. And so you want to perform some encoding into some subspace such that you are able to detect and correct errors before they propagate to the system and you lose information. And it's quite fascinating that you can build sort of like an error correcting code, build up just some very simple building blocks such as these poly matrices, but they can have deep connections to, for example, these topological phases of that. So for example, a well-known error correcting code that people often like to use is the so-called toric code. And the toric code, you can think of it as some deconfined D2 gauge theory plus one dimension. There are also other types of interesting error correcting codes where we don't even know whether there is a nice TQFT descriptor or even a nice QFT descriptor. So an example is the so-called hot code, and the sort of excitations that are allowed by this model don't live on some sort of fractal lattice structure. So even challenging for us to try to build a sort of continuum limit for these kind of models. So the relation between topological phases and error correcting codes is a deep relation, but we still need to continue to explore them. Just so that I could get everyone on the same page, I've attempted to make this a three-way dictionary between what people usually talk about in different communities, but hopefully is sort of the same thing. Starting from the quantum information side, what they would say is you sort of have you start with some Hilbert space, which is some qubits, and you define so-called poly group, defined as the poly operators on each side. You can then define something called the stabilizer group, which is a product of a set of commuting polys. And in terms of condensed matter, you can take that stabilizer group and define a so-called stabilizer Hamiltonian, where you give an energetic penalty to any term that violates your stabilizer. The ground state of that Hamiltonian is so-called what the quantum information people call the code space, which is just the span of all the eigenvectors which have eigenvalue +1 under these stabilizers. Since they all commute, you can always set them to +1 at the same time. In high energy, you would think of some topological quantum field theory, and the ground state subspace would be sort of the Hilbert space you get manifold and you construct a cone of that, you can take the partition function and evaluate it on that cone, and that would be your subspace. Your sort of filter space. Now, what quantum information people call the logical operator, what they would say is among all these stabilizers, let us find all the polys, set of poly operators that commute with all the stabilizers. The way I'm writing it here is sort of like the centralizing the poly group. And in terms of condensed matter, people would think of, you have this Hamiltonian, let us find what are all the symmetries, or what is the commutant of this Hamiltonian? What are all the terms that meet with this Hamiltonian? And we should think of those as symmetries of a Hamiltonian, which allows us to sort of diagonalize our Hamiltonian into these sectors. If these codes correspond to topological codes, which I'll find in a bit, you can sort of think of these symmetries of the Hamiltonian as higher form symmetries. And there's a little subtlety on the lattice and in the continuum of what a higher form symmetry is. But what you really want to, there might be some subtlety on the lattice on whether there's sort of these contractible, homologically trivial or non-trivial loops. And that's sort of this distinction I'm making between spaceful and topological. If you sort of quotient out by these homologically trivial loops, then the only ones who care are the ones that are topological, and that's what the quantum information people call logical representations. So you quotient out by logicals that are or themselves stabilizers. So you notice that the stabilizers commute with themselves, so they are sort of symmetries of this Hamiltonian. But there's sort of these local ones that you want to quotient all of them out, and if you quotient out, you will get a logical representation. So you only want to care about the equivalence class, which is, you can think of it as making this symmetry topological. And what is the dimension of this ground state subspace? Well, the ground state degeneracy of this space, you can sort of count that by as it's just the dimension of this code space. And you can also, there's a nice way to think of it in terms of the number of logicals after you quotient out all the stabilizers. Okay. And the ground state of degeneracy of a TQFT of course just the recursion function on that manifold with an extra time limit. Okay. And there might be some confusing terminology, but at least in quantum information and condensed matter, people define these topological codes as local stabilizers, like these logical representatives are non-local. And this does not exclude these sort of weird fractal models, which are not fully topological, but some people also call these topological. Okay. So hopefully this is sort of like a dictionary between the terminologies of different fields. And the most the simplest one is the so-called Z2 toric code, which is the toy model for Z2 topological order. And the Hamiltonian, just to get everyone on the same page, is this composes of a vertex term and a Floquet term. For each vertex term, you put all the poly x's around a vertex, and for the Floquet term around every Floquet, you put a poly. And these terms always commute. And so if you are on the torus, you notice that all the product of all the vertex terms separately and the Floquets separately are 1. So that gives you a ground state degeneracy of 2 to the 2 on the torus. And the excitations of the toric code are the so-called charge and fluxes, and you can think of them as violations of the vertex term. So we call it E and M, and to create an E, you just apply the blue string here, means the poly Z, supply a blue string of poly Z around the direct lattice, and the endpoint post E excitation. On the dual lattice, you apply X's, and the endpoint post M particle. Okay. So now this is all understood. Now, if you ask a quantum information person, they might argue, well, this is actually not a toric code we actually do in an experiment in the lab. They would say this is a toric code. You would actually have to not only have this sort of model, but you would also have to measure these stabilizers and use them to correct for error. error or an X error. So what you have to do is you actually have to constantly measure these operators. And so you would have, for example, you can measure all the X operators at the vertex terms at the same time. You would use that to detect if there were any Z errors in your system and then correct them. And then the next round, you would measure all the Floquets at the same time and use that to detect that. And you have to repeat this detection and correction in order to ensure that your memories, your quantum memory is intact. But now this actually raises an interesting question. We're going to measure these operators and correct them. It seems that we're just repeating the same measurement over and over again, and they're commuting measurement. Is there any sort of anything more interesting? Can we sort of different types of measurement at different rounds, and sort of can we come up with different type of error correction in this way? And so two years ago, Hastings and Ha came up with an actually interesting proposal. They call it the honeycomb code, but due to its sort of periodic nature, people have been calling these Floquet codes. So let me just explain what the setup is. So they said, let's put qubits on the vertex of the honeycomb lattice, and the schedule is consists of 3 rounds. The first round, so I colored the honeycomb lattice red, green, and blue, and the Floquets are red, green, and blue, and the edges are colored by edges that connect the red Floquets together, for example. So looking at all the red Floquets, for example, with round 1, I would measure a 2-body operator XX on all the red edges. Second round, I would measure all the green YY operators. Round 3, I would measure on all the blue edges the ZZ operator. So this is how sort of like the schedule of measurements would sort of look like in time. And now you can already notice that the measurements don't commute. And what's funny about this is that usually in error correction, you think of putting everything in one subspace and trying to keep it in that same subspace. You don't want stuff to move. But here, because you're measuring non-commuting things, your subspace will keep changing from round to round. So that's already interesting, and already raises the question, if we want to make connections to TQFT, what does that mean? Because now your subspace is not the same anymore. But let me explain how sort of this error correction or sort of like works first. So the first thing to notice is that there's, in addition to these measurements, there's still some constants of motion of this measurement dynamic. So for example, using information of the first round and the second round, if you look at the blue Floquet, you notice that there are red edges and green edges. So if I take all the products of the red edges and of green edges together around this Floquet, you notice that I have 6 X's and 6 X's and 6 Y's. Maybe this is a bit hard to see, but you get 6 D's around this blue Floquet. So that's just the product of 3 red operators and green operators. That's a product of C's, and you notice that this operator actually commutes with all 3 rounds of measurement. So once I infer the value of this Floquet, that will stay out constant throughout the dynamics. Similarly, by symmetry, from the green and the blue round together, you will measure this red Floquet of X's, and from the blue and the red round, you measure the green operator of Y. So this stays constant throughout the dynamics, which means I can still measure them. So I infer them from the product of the measurement output. And once so I can still use this as sort of stabilizers to detect for error. So if I see that one of these values change, it means that an error must have occurred somewhere, and then I can try to figure out what type of error caused that, try to correct that. So this is how error correction works. But now, what is the relation to sort of the toric code we're using? So let's look at, for example, one of the rounds. So suppose I repeat this multiple times. After a while, you would get that, for example, round 1, the wave function I have will be a simultaneous eigenstate of all these red edges and the red, blue, and green plaquette. Okay. So after some multiple time on rounds 1, 1, 3, this is sort of how I describe my state. They're sort of the plus minus 1 eigenstate of these operators. The claim is that actually this set of states, this set of stabilizers, you can actually map exactly to the toric. So secretly, after some number of rounds, you initialize a toric state, and you're actually jumping between different instances of the toric. So let me show how you see that. So after around a bunch of rounds, on round 1, 1, 3, these are the stabilizers of my state. I can restrict to a simpler subspace. So let me try to set all these edges, these red edges. There's one stabilizer per edge, but you notice that there are 2 qubits here. So I have one constraint, right? But I have 2 qubits, so I could have effectively in that subspace 1 qubit left. So I can write down what is an effective algebra for the 2-dimensional space, right? So I can write that as spanned by poly X and poly Z. And those 2 operators could anti-commute with themselves and also commute with this XX. So you can write that down. There are 2 representatives which only differ by a multiplication by this operator. So it's XIX or XI you can choose. But now if we look at these operators, you can see that, for example, for the red operator, which is a bunch of X's around the red plaquette, you notice that the edges pointing out of this red plaquette or red edges. So this is an X and an identity, so you get an X effective on this red one. And now if you look at the honeycomb lattice I drew earlier, you can go to the superlattice and you see that this operator looks a lot like a vertex curve. And similarly for the green and the blue plaquettes, you can see that the Z effective is either given by ZZ or by multiplying by XX. This is a YY operator. So for every red X, ZZ becomes an effective Z, and that's basically the plaquette operator. And similarly, the green one gives me another plaquette, but in a different configuration. So this is how you show that in each round, you're actually secretly still have a toric code. But the funny thing is, you have this toric code on this red superlattice. Once you go to the green measurement in the next round, you will have a toric code on the green superlattice. And so you're sort of jumping between different toric codes of different colors. So let me pause here in case there are any questions. So it's only been 2.5 years since the honeycomb code came out, and there has been a lot of excitement regarding these new error correcting codes. One nice thing about this Floquet code is that for practical purposes, at least, instead of using 4 volume measurements that we would use for the toric code, everything here is 2 volume, so that reduces the overweight and might be more friendly with architecture, for example. And there has been a huge explosion of works on trying to understand what else you can do, from benchmarking these properties to, for example, constructing new examples of Floquet codes. What are the properties of Floquet codes, relation to measurement dynamics, do computation with Floquet codes. And actually, if you go onto YouTube, you can actually learn about the history of the honeycomb code. It's 2.5 years old, but apparently, yeah, you learn about the history of it. But what I'm going to talk about today is sort of motivated by these results. One thing I'm going to explain in a bit, which is in the original paper, but I'm going to show you a much nicer way to see this, is that it turns out that there are 3 rounds of measurements, and after you complete 3 rounds of measurements, come back to the same sort of effective particle, for example, on the red lattice. But it turns out that if you follow one of these logical operators, like a string operator or E, and you follow it throughout the cycle, it turns out that E turns into M. So there's some sort of like automorphism that is swapping E and M throughout this measurement dynamics, which is very interesting. But the motivation for us that started our project is that this EM automorphism is sort of like a Hadow market. It swaps a logical X with a logical Z. So the question is, can we sort of use this to our advantage? Since you're going to be doing measurements and doing error correction along the way, can you find some sort of sequence of measurements such that when you come back to yourself, you perform some automorphism, which will be realized in a code as a logic. So in addition to doing measurements, you will be able to do quantum computation. So in usual error correction, you would in usual like codes, you would do error correction, and then after you make sure you have no errors, you apply some unitary gate to do computation. But they're sort of two separate models. If you can find a way that we're doing that at the same time, then all we need to do is measure. So there's no unitaries at all. But somehow we can do both error correction and computation, and that would be a very powerful. So that's the motivation of our work. And what we figured out is exactly what I just told you, and we sort of call this dynamic automorphism code. So sort of a long name, but the fact is that we call it dynamic because your schedule does not need to be Floquet, or it does not have to have periodicity, depending on sort of what kind of gates you want to perform. Suppose I have some computation I want to perform in a quantum computer implemented by some unitaries. For each unitary, I would give you a sequence of measurements you would perform in time, such that it is after you come back to yourself, you implemented the design unitary. And the only thing you need to do is now stack those measurement sequences up together. And so you get a dynamic sequence of measurements, and each measurement implements some automorphism in your underlying field, and that automorphism is realizing it.
So, like, I'm guessing, like, you would be able to do operations within a single qubit, like single qubit ones, but there's also ways to do 2-qubit gates this way.
Yes, yes.
And then you'll have to merge and stuff. Or...
Yes, yes. I'll briefly go on how to do that. So, in some sense, you can perform by using measurements only. You can perform error correction and computation at the same time, and sort of this is sort of a new model of sort of measurement-based quantum computation. So, but along the way, I'll also make connections to how to think of all of this actually very nicely in terms of TQFT and your familiar stuff. And the main idea, sort of the take-home message of how to relate this to TQFT is the insight that measurement, you should think of measurement as performing anion computation. By sort of performing measurements, you're sort of proliferating little anions to the top around your lattice, and that performs condensation. And so you can think of, for example, starting with some parent TQFT. Let's say this direction is time. I forgot. Time is going upwards. And let's say we do two different condensations. Condensation A that proliferates anions type A, and A1 and type A2. And let's say you get some effective model, some child, and let's say the two child are the same TQFT. But it is possible that you have a domain wall which is transparent from both sides, meaning and any excitation here or anion I can push through in time to become a different and possibly different anion automorphism on the other side. And in terms of quantum information, it means that any logical information, because it's encoded in terms of the statistics of anion, is preserved throughout this dynamic. And the fact that it can push the anions through means that quantum information is preserved. And I'll give a more explicit example how to see that in a bit. But this is sort of the key idea. And from this, we can figure out how to do quantum computation as follows. You choose some sort of parent theory, and you sort of find all the condensation that give equivalent child. Then you just sort of figure out, I'm drawing these arrows between any pairs where this domain wall is transparent, meaning I can push anions. So it means that logical information is preserved. And so this gives me some sort of measurement sequence I perform. I'm going to walk on this sort of graph. Once I come back to myself, I can compute what automorphism I accrued throughout that process. And if that automorphism is non-trivial, I perform a non-trivial gate on my code. And then this is a separate thing, but when you build error correcting code, you still need to show that it's error correcting. I might not talk about too much of the details, but that's something you have to check separately, and that's not given as is. So this is hopefully the take-home message of the idea of what I'm going to be talking about. And then now I'm going to go through some of the more detail. Yes. So it just means that they're isomorphic. So there's two TQFTs that are isomorphic, but you might want to describe an isomorphism between the two tiles. And once you so in more technical terms, every of these arrows is isomorphism. And you can compute a closed loop, and that gives you an automorphism. So you given some isomorphism which is fixed from this construction, do the closed loop, that gives you an automorphism, which might be non-trivial. And in the quantum code, that corresponds a lot.
You know what it means categorically for those two terms to be isomorphic? If I think of them as local hypotheses.
Local by one. You could say it's invertible. The most precise way to say it is possible sum of invertible. It might be a direct sum, so it might be a simple object, but you just want them to be a sum of invertible. But typically it's invertible. When I say sum, that's very technical. Transparent, if even it's a sum, you can still push things through, even though it's not invertible. I'm saying, so what I mean is, you perform a sequence of measurements, you're jumping between different instantaneous stabilizers. After some number of rounds, you come back to yourself, the same stabilizer. And you can check at the logical level, did the logical operator undergo compaction? And if it did, then you have applied logic. Yes, it is quite counterintuitive. Yes. So it turns out that there's some special condition that you have to impose in order to ensure that, for example, you can go between effective torical, say the red lattice I talked about, to the green lattice. It's not clear a priori that this effective operation will be sort of unitary. But actually, it turns out that if in the QFT at least imposes condition that in switching any on group on the lattice, it will turn out that you can preserve logical information. So there's actually an equivalent unitary evolution that will take you. I haven't shown that. That turned out. So it's sort of quite counterintuitive, and we need to impose something. But at the same time, that's what's cool about this measurement. Any other questions? So if not, the outline. I'm already halfway through, but I guess the outline is following. I'm going to talk about something called the color code, which might be less familiar to field theory people, but it's a very nice lattice model that sort of shows you all the symmetries of sort of two copies of the force, different sort of realization, but has all the nice implicit symmetry. I'm then going to talk about how you can think of measurements as anion condensation. And then in this particular model, I'm going to tell you how to think of automorphisms from these sort of measurement sequences. And if I get to the end, I'll talk a bit more about how you can construct these codes and how in quantum information there's something called the Clifford group, which is sort of like operations that send poly operators to poly operators. And more in 3+1D, I'll talk about how to get a non. So let me start with this. So the color code is a stabilizer code. It's defined on the same honeycomb lattice with 3 colors. And the stabilizers, I are generated by 6 body operators. So there are products of x, y, and z on the plaquettes of this for all the vertices. And so there are 3 colors and 3 polys, and so these are the stabilizers, and they all. Now, what are the excitations of this model? So suppose I act with a poly x on one of these. This is going to violate some of the stabilizers. For example, on the red plaquette here, it's going to violate both the y-type stabilizer and the z-type stabilizer. Just so that it's easier to notate, I'm just going to call a plaquette violated, but using an x operator on a red plaquette Rx. And similarly, so this will, a single x operator here will create Rx, Px, and Px from the vacuum. So in terms of super selection sectors, you have these 3 non-trivial anions, but they fuse to their end, so they're not really. And similarly, how do I create a single Rx excitation? I would apply 2 x's. Now these 2 green and blue plaquettes are happy, but now I've created only a red x excitation. And you can see also there's a similar thing that if I take a 2-body x times a 2-body y times a 2-body z, that's just identity of the cell. So I can create Rx as a pair, Ry as a pair, Rz as a pair. They should all fuse to the identity also. So the excitations of the color code, you can encode it very neatly into this magic square. So there are 9 bosons in the color code, and they have this property that, first of all, the product of all rows and columns are identity. That follows from what I just showed you. Second property is that the color code, the bosons of the color code, you can match exactly to 2 copies of the core code. So you can stare at this square and also notice that the product of every row and column here for 2 copies of the core code is also identity. Third property, I messed up the numbering here, but anions braid according to Uno. So every anion here braids trivially if they share the same color or the same column. So that is if they share the same row or the same column. So you can also see here, for example, this one will braid trivially with these 2 and these 2, but will not braid trivially with the remaining. So you can see that on the lattice, the way I've written the color code, it makes sort of a lot of these symmetry of 2 copies of core codes that are matched. So this paper very nicely points out that in the Floquet code that I just talked about previously, you're performing 2-body measurements on this honeycomb lattice. And so you should think of this measurement actually performing a condensation in the color code. By applying these 2-body measurements, you're going to proliferate these Rx excitations all around the lattice, and that'll perform condensation. So what happens is you condense this Rx excitation. It confines all the anions that braid non-trivially with it. And now equivalent anions up to fusion with the thing you condense becomes a new superselection set. And since I pointed out that the color code is equivalent to 2 copies of the core code, you condense 1 boson, so you're left with 1 copy of the core code. And these are the remaining superselection sector, and that's 1 here. Okay, so that's why we're left with 1 copy of the core code. And now, so you can see that different rounds of measurements, the reason we're obtaining a toric code, but on different superlattices, because we're condensing different bosons. So now let me show you how to compute these automorphisms for measurements. And also I wanted to show you how the logical information is preserved. So the measurement schedule in the honeycomb code is for red, you condense red X, green Y, and blue Z. So let's sort of track this sort of path. So I start by condensing red X, and I happen to let me track this anion, which let me call in the toric code, and let's track that throughout the dynamic. So for example, if I go to the next round where green Y is condensed, you see that there's this anion that is equivalent, the vertical one and the horizontal one, which is the different one. But you can see that they share common representative, which are Y. So I should label this as E. If I go to the next round, Ry gets confined here, But if I choose a different representative for the same anion by, it actually survives. So I can label it this one. And then in the last round, I need to update it into dx, and dx becomes this one. So after you track through the whole dynamics, you realize that the P anion turned it into an M anion. So by just tracking this based on thinking of it as a color code, you easily see why one, logical information is conserved, because through each round, I can always push one anion through another to the other layer. And second, why this why E turns into M after one round. One round in this schedule. Okay. So you can think more generally. I could have started with condensing this anion, but the next round I could have chosen any sort of other anion with based on trivially with it, and that should be an allowed move too. So then I can sort of jump along these path condensation. So what is the sort of path I can take along this graph look like? It turns out to look like this. So you can put this graph very nicely on a torus, and there are these 9 condensations, and they're connected with stuff. So you notice that one of these anions is always connected to something with a different poly or a different color. Okay. And the original honeycomb code is just the one that goes around the torus here. And so just walking along this graph will already give you some sort of dynamic version of the torus. Now, one thing that's interesting that we came up with, and also in this independent work here, is something called a CSS honeycomb. So, CSS is a bureaucrat, and this means that you only need X measurements or Z measurements. But you can completely get rid of the Y measurement and just follow this path here. So you just alternate between red, green, blue, and then alternate between X and Z. That's also an allowed block. And something interesting about this model that you will need to stare at the lattice to see is that unlike the original honeycomb code, there are no permanent stabilizers. So one of these Floquets you measure might get scrambled at some other point in time. But the interesting thing is it is still error correcting because it turns out that one of these Floquet operators always gets measured again. So you get to compare them before it gets scrambled with the next one. So as long as you are able to compare them at 2 points in time before they get scrambled, you can still detect errors and use them. So that's one of the cool things. More generally, it turns out that there's something cool, very cool about this torus structure that I pointed out. So it's as if this torus has an EM automorphism in one of the cycles. So it turns out you can show that if your path went around this torus in a non-trivial cycle, you would have implemented an EM automorphism. If it's a homologically trivial cycle, then you would not implement the EM automorphism. And for example, the CSS path, it goes around both cycles, so you get EM twice. So you can, thinking about sort of this graph and the paths you can walk, allows you to see this structure very explicitly, and also allows you to do the same thing.
So can you give an example of a path that wouldn't be error corrected?
Yes. So right. So this path does not guarantee anything at all at the lattice level that will be error correct. So for the lattice model I've chosen, it turns out that you sort of want to go through all the 3 colors in order to error. But that does not guarantee that. For example, if I went to a different lattice model, even for, let's say, instead of the color code, go to the 2 copies of the color code, and I naively do this measurement, it won't be error correct. It's not really guaranteed. So it's just a nice way to frame things, but it does not show error correct. Check that for separate. So now let me show you how to get construct these dynamic automorphisms and how to get the Clippers. So I've shown you how to, starting from the color code of the parent, which is equivalent to 2 copies of the toric code, we perform some condensation of one boson to either get trivial automorphism or a non-trivial automorphism, which swaps EM. Now I want my child to be the color code, which is 2 copies of the toric code. And does anyone know off the top of their head how many automorphisms there are in 2 copies of the toric? 70. So, so there are only 2 of them here, but surprisingly, there are 72 automorphisms in the color codes. And let me show you a bit why that is, but it gives you a sort of plethora of possibilities of things you can walk around. But it turns out that at the lattice, I only need my parent to be 2 copies of color code. Let me show how that works a bit.
What is the size of the generator of this?
Sorry.
What is the size of the generator of this 72?
Yeah, that's this one.
Okay.
So what is the full automorphism group? It turns out to be so the boson, you just need to permute all the bosons in the color code. And by looking at this table, one nice way to see it is that you can permute any of the colors with the rows, you can permute any of the columns, and each of that is one of the S3 group. And then you can also swap color and poly. That gives you a Z2 that swaps. So that's the full group. That's the order 72 group here. For a quantum information person, you might be more familiar with another fact that the group structure is the so-called real Clifford group of 2 qubits. And the way to see it is that this group is actually generated by 3 operators, the so-called Hadamard 1, Hadamard on the first qubit, Hadamard on the second qubit, and Xenon. So roughly in terms of anyons, you should think of it as a toric code, the 2 copies of the toric code, and roughly, if you think of M as poly X and E as poly Z, then the automorphism that swaps E and M is like a Hadamard. And then there's this so-called 2-qubit gate Xenon that does this automorphism. And it turns out that these 2 generate a full Clifford group that is real on 2 qubits. And that's exactly the same 72, but written with different generators. So this is the automorphism group I want to implement. If I can do this, then at the logical level, I can perform, for example, this real Clifford group on my logical qubit. So how do we get that? So at the lattice level, my parent I'm starting is 2 copies with color code. And there are 2 sort of condensations I can do at the level of the lattice. The first naive thing to do is at each copy, you just do the 2-body measurement. So by the way, the setup I have in mind is sort of this bilayer honeycomb. And now if you just measure 2-body operators in each layer, that'll just give you a toric code in each layer. So that's sort of the naive thing you can do. The second thing you can do is you perform a vertical measurement between the layers. So for example, a Z1, Z2. And if you started with the color code, that sort of reduces you to an effective color code, which is sort of the diagonal that's remaining. And now you can start, for example, let's take color code, this effective color code as our home base. We walk around this graph and we come back to ourselves, we can check whether we get an automorphism. Now, I mentioned that we want this Hadamard 1, Hadamard 2. That's already given by this AC harmony code. We just need to jump to one of these toric codes, go around a loop that's the EM automorphism, one of the copies, and then off that. That'll already be there. So the only thing I need to do is figure out how to do the Xenon gate. There's two pieces. Okay. And if you think of the Xenon in terms of the color code, what you want to do is you want to swap the green and blue rows. And it turns out one way to do that is let me start with a sequence, which let me secretly replace it with blue first. You're just noticing that the thing I'm measuring is going forward and then going backward. That'll not implement automorphism. But then it turns out if I change this to green, and you can go through this computation and compute what automorphism you get, it turns out that it'll swap the blue and green as well. Yeah, I haven't shown you how to do this. So we've obtained the real Clifford group. That is still not the full Clifford because it does not obtain, we still cannot say, for example, this so-called S gate. An S gate is a gate that swaps poly X and poly Y. But in terms of anyons, that doesn't really make sense because that's like turning an M, which is a boson, to an F, which is a fermion. But it turns out there's some tricks you can do, which allows it's so-called, if you put this color code on a manifold with a boundary, there's some sort of different encoding in which actually allows you to do the S gate. And the architecture we put that on is sort of like like this triangle. So there's sort of a color code with a boundary that's very similar to sort of like how people store code on different condensed boundaries. There's sort of 3 condensed boundaries you can put here. The boundary on the top condenses all the Z-type bosons, so RZ, GZ, DZ, and then similarly for Y and X. Now, it turns out that this encodes exactly 1 logical qubit, and the way to see that is you just need to count the number of logic wafers. So, what is logic X? You create an RZ from to the boundary, and you move them to the bulk and fuse it. And similar for YZ, changes to green and blue. And you see that the red and the blue, if you put them on top of each other, they'll anticommute exactly what you get to see. So this encodes 1 logical qubit, and I've already showed you how swapping green and blue can be done. But if you look at the way it acts on the logicals here, it actually just swaps this Y and Z logic. So by permuting the colors, you can just swap any of the other 2 colors. So for example, if you swap X and Z, that would be catamorph. Swapping X and Y, that would be S gate. So you can do all the 1 qubit flicker gates. And how would you move on to n logical qubits? Well, you would just have a stack of these triangles. And it turns out that there's a measurement sequence that couples the 2 triangles together to give you, and there's a measurement sequence that couples the 2 triangles together that performs an entanglement. So you can sort of think of this like a stack of tortilla chips, and then you can somehow get a quantum computer by middle. In the paper, we figured out all these microscopics. I won't bother you with the details, it's quite horrific, but the take-home message is that all of our measurements are still 2 qubit, except at one of the steps on one of the boundaries for this entangling gate that we need 3 qubit. And otherwise everything is still a 2 qubit measurement. So it's very sort of friendly to an architecture where sort of 2 qubit measurement is sort of the native operation.
Before you, in the previous geometry, where you weren't using the tortilla chip, it was all 2 qubit.
It was still all 2 qubit, but you couldn't get all of them. You need the boundary set. So lastly, let me mention how to get an interesting non-flicker gate in 3+1, and that involves going to the 3D color code. You can probably guess the story by now. In 2D, I want 1 color code which includes 2 copies of the core code, and the parent is 2 copies of the color code. In 3D, the color code is equivalent to 3 copies of the core code, and the parent I use 3 copies of the color code. The color code, just I won't go through the details, but the color code is something similar defined in 3D, where you have sort of these 3 cells that can be colored in now 4 colors. And stabilizers are given for X stabilizer for every 3 cell and Z stabilizer for 3 cell. And it turns out to be equivalent to 3 copies of the color. Now, interestingly, there is a non-flicker gate you can get, in the 3 plus 1D color code, which is equivalent to 3 copies of our code. There are two ways to explain it. And this was sort of first pointed out in the quantum information theory by Benny Yoshida. We've recently written about how to think of this as in the high sort of the field theory language. So let me start on the QI side first. It turns out that in 3 copies of toric code, there's a so-called transversal control Z gate, which does the following. At the level of the logicals, you can think of the X logicals as sort of the membrane in the toric code. And what happens is this X1, after you apply this control Z gate, will become X1 times control Z2. And similarly for the other two. You can think of this in the field theory as actually a transparent domain wall corresponding to an SPT phase. So along this domain wall, you can think of it as there is a defect given by this 3 cocycle, where A here is a 1-form gauge field for this 3 copies of toric code. So for the toric code, I'm just writing the Lagrangian, and B here is a 2-form gauge field, A is a 1-form gauge field. And what this domain wall does is if you push M, which is generated by 2-form B, B will go through and we'll get an extra A2 cup A3. And this A2 cup A3 is a codimension 2 defect. So you push codimension. So sorry, I'm drawing this in space, by the way. But in space-time, this would be a membrane. You push this through, you get another membrane, which is given by this defect A2 cup A3. And that's the exact analogy of what's happening in the quantum information side. V is the analog of M, which is generated by column X. And this interesting defect here has been known in the quantum information community as sort of control Z operator. So this is an interesting automorphism that can happen in 3 copies of the toric code. And that actually gives us some intuition why non-Clifford gates need to go to the 3 plus 1 in it. So there, in quantum information, there's actually sort of a theorem by that says that if you want transversal gates in 3 dimensions, non-Clifford gates usually go to 3 dimensions. And the intuition for that is basically it's only in 3 dimensions that you have a membrane operator that can turn into this interesting defect that you wouldn't really write out naturally in a lower dimension. So this is a sort of a defect that is sort of a condensate of particles in a sort of related to some SPT. So this is the automorphism we want to implement. The rough argument just basically goes similar to this green-blue swapping I told you. I won't spell out the details of the lattice, but it turns out that you sort of find the sequence that you move forward and backward, and you change one of the final steps into this sort of version. So in the color code, it turns out that instead of a control Z gate, oh, this is the typo. This is a transversal T gate in the color code. And what happens is instead of doing an X measurement, you would sort of do a X measurement that's rotated like so something like X plus Y. So you measure in the X plus Y axis instead when you go back, and it turns out you can check that you can obtain this concept. So let me conclude. And so what's would be interesting to figure out in the future, for example, let me start from the quantum information side. So I mentioned in 2D how we could get all the Clifford gates. In 3D how to get a non-Clifford gate. There would be some techniques that people know on how to sort of jump between dimensions, sort of switch between a 2D code, 2 plus 1D code, a 3 plus 1D code. If we can do that, that might be around towards universal quantum computation in these dynamic codes. It would be interesting to figure out how to do error correction and fault tolerance, especially since in these models we don't have sort of periodic dynamics. So usually how people do fault tolerance is they map to some statistical mechanics model, but now the statistical mechanics model does not have any translation in there. How to approach that. It would be also interesting to tackle these so-called good LTPC codes, which people have been recently excited about. They don't seem to correspond to topological codes, or they live in extremely high dimension. But if we could figure out how to do the dynamic version of LTPC codes, that would be really interesting, because people don't really know how to perform computations in LTPC codes. And now on the theory side, in case any of the TQFT people here might be interesting, what I've shown you is that starting from a parent theory, you can do different condensations, you can go to different childs with, that are isomorphic to each other. And by walking through some path of isomorphic theories, you can come back to yourself and actually implement it on. So for example, one might consider constructing some version of this for some non-abelian annual theory. You could start with some non-abelian parent, try to do some condensation, and to see, is it possible to sort of get all the automorphisms in this sort of stuff. There might be also some Floquet codes where maybe you don't need to think about the parent. This is just one way that I've used to understand this, but maybe there are other codes you can construct where you don't necessarily, or cannot even think of it as parent code, but it's interesting to come up with such constructions. Okay, I think that's all I have, so thank you very much.
In general, you also have like surfaces that don't do automorphism, like some anions will get stuck. Would they be useful at all?
In that case, I would say that the quantum information is not reserved from round to round. So that wouldn't be, I mean, you could kill partially some of it. So for example, we have this construction where it jumps into sort of like a fracton location, and it jumps between different rounds, but each round, the corresponding theory has different round states. And so it turns out that you only sort of you're going to lose some of them, right, when you go from the bigger theory to the smaller theory, but at least the information in the smaller one is still very broad. So that's still okay, even though we're looking at
Two questions. So one is, and just to be clear, this non-Hilbert gate, is that so you combine that with the other gates, is it universal or?
It is universal, but the trouble is the 3 dimensions alone. You don't have the Hadamard gate because you cannot swap again. It's hard and everything. So in 3D, you only have non-Hilbert gate, but that's not enough.
Other the problems sort of construct the happen.
Yes, yes.
The other question was, go back to that 3D discussion. Just want to understand you have this, you wrote down this automorphism that says B. Okay, so on the left hand side you have this thing with B equals B plus A. Okay, but then over here you have some operation on logical qubits.
Yeah.
I just want to understand slightly more microscopically. So what's happening there? So is there some like membrane operator that's changing into a membrane operator or something?
Right, right. So in space you would have a membrane operator, and you would sort of, you can think of sweeping this defect, which is like applying a zero form symmetry. So that looks something like applying control Z to all segments, or all triplets. And then what happens is you get an extra membrane of control Z on the 2-3 copy right next to it.
So a membrane is going from product of 2 membranes.
Yes, you get a product of 2. And yeah, and actually, maybe a cool thing to point out is that there are these membranes of different dimensions. For example, you can further take this control Z and act it on X to get another Z. And that corresponds to like taking one of these defects, and now it's like a one-form symmetry. You apply a one-form symmetry, and when this control Z membrane intersects with another X membrane, you'll get a Z along the intersection. So that's how you would get a control Z gate. And actually, this sort of applying different symmetries in different dimensions to get another symmetry is basically what a hierarchy is. And actually, so all of these symmetries together in a topological stabilizer code actually form information people already know, but we're porting it back. Yeah, that would be the goal. And I don't have the belief yet, but maybe one way to construct maybe start with how you still try to do some measurement. I don't know whether it's still on your account. Yeah, but or you could start with maybe the child being able to see what the thing is. And might also just give that measure. I think it is that that one be one way. But yeah,
Would you require like the Tamil graphs to be like tricolorable or something? I guess that's for the old honeycomb, maybe for your general honeycomb.
yeah, for this double bilayer color code that was not the case, and also this 3D for colorful. So, yeah, I don't see the demo.
So for the question,